These three video demonstrations aim to show the power of conducting structural FEA of a design within the Open Meta toolchain. This integration allows a component to be automatically subjected to a static analysis with various metrics computed. Shown here are generated contour images of two such analyses of a single part with different applied loadings. They show the component displacement of each analysis noted by the different scales. This concept can then be expanded to analyze large design spaces with metrics and their relationships visualized in the Open Meta dashboard. The dashboard visualizes the metric outputs for each component configuration in the form of parallel axes and multivariate plots. These plots aid in design decisions by allowing an analyst to compare huge numbers of data points in one location. For this first video, we will go through and demonstrate how a user can set up a CyPhy static analysis test bench through the Femap application interface. To start, we will go over what needs to be defined within a component model in order to initialize a Femap session. In this demo, the analyzed component is a standard bracket. The component model must contain a reference to a parasolid CAD file. There are also interfaces within the GME CAD model that reference geometric features in the solid model of interest to the user. These interfaces can be surfaces, curves, or points that the user may want to apply loads or constraints to. On the right is the bracket parasolid file referenced in the component model imported to Femap. The image on the left defines the interfaces for this class of bracket. In GME for this component, these interfaces are defined by points whose coordinates are along surfaces of the various cylindrical holes for each interface. The coordinates of each datum are stored in a JSON formatted file associated with the component and is shown on the left. As an example, this file tells the Femap application that the interface 1L-S1 datum is located on a surface at this location. These coordinates point to the surface the cursor is hovering over in the Femap model. The final thing each component needs is to have a parameter defining the material associated with the component. This parameter value is one of the materials within the Open Meta material database. To push this component into a Femap session, this bracket should be referenced in a component assembly. Let's call it bracket. Typically, the Femap session would be created to analyze a component's performance in a multi-component assembly, but for now this functionality is limited to an assembly of a single part. This assembly is then referenced in a structural FEA test bench. In this case, the bracket assembly is the top-level system under test or assembly to be analyzed. The bracket component that is referenced in the assembly is inserted as a test injection point or component within the top-level system under test that is of interest for this current analysis. Finally, a Femap workflow object is referenced that will notify the system that this analysis uses the Femap application. To launch the Femap link session, the CyPhy Femap link interpreter icon is selected. The resulting dialog box presents options to capture mesh-related events, as well as asking if you would like to save the Femap model upon exit. Neither are required for these demonstrations. The interpreter creates a Femap instance and initializes the model. After importing the component geometry, the coordinates in the datum mapping file are queried to map the datum names that are known to the CyPhy test bench to the points, curves, and surfaces that are known internally to Femap. The macro also creates a material card with the necessary material properties populated as defined in the Meta material database. A p-solid property card is then created which references this material. At this point, you apply loads and constraints to geometric entities just as you normally would if using Femap as a standalone product. To apply a load, you create a load set and load definition. You then select the surface you would like to apply the load to, say interface 1L-S1. Here you can see that the Femap surface ID 1 has been selected. Looking at the add-in form application, which logs information from the link session, we see that ID 1 does indeed correspond to the interface 1L-S1 datum. We then give the force load a name, say load 1, and set the value to 8,000 newtons in the negative z direction. Once accepted, we see that a corresponding force load construct has been created in the test bench. This load is applied to a face or surface that is associated with the interface 1L-S1 datum, just as expected. Looking into the force load, we see the negative 8,000 value. Now say we realize we actually needed a load of negative 16,000. To correct this, we simply change the value. Going back to Femap, we see the logger has detected a change in the load. Editing the load, we see that it has been updated in the Femap model as well. While the load can be modified in either Femap or CyPhy, this demonstrates the bidirectional communication between the CyPhy and Femap models. Constraints are created similarly to loads. We create the constraint set, say constraint set 1, create a constraint definition, and select the desired surface. Here we again see that the selected surface ID of 5 is mapped to a testbench datum interface 4S1. Currently, the Femap link session only supports the adding of constraints with each translational and rotational component defined explicitly. We do this through the arbitrary and CSys option. To create a fixed constraint, we simply check each component box. Just like with the load, upon application in Femap, a displacement constraint is created in the test bench and points to a face associated with datum interface 4S1. Looking at the constraint in more detail, we see the components are indeed fixed. At this point, everything we need to execute an analysis is complete, so we close the Femap link session by selecting the CyPhy Femap link interpreter again. What we have accomplished is setting up a testing scenario to subject a component to a static analysis, and up to this point, everything done could have been done without the use of CyPhy. The real power of the tool comes with the interface concept. While the interfaces are defined with coordinates dependent on the component geometry, different component geometries may be considered under the same testing scenario so long as they also contain similar interfaces. So while the location of the interfaces may change among geometries, if the interfaces exist, the loads and constraints may be applied programmatically without concern of the actual model geometry. As an example, say we wanted to apply this test scenario to bracket 6. To do this, we simply drag the bracket 6 component and drop it onto the bracket 5 reference in the component assembly to redirect the reference to the other bracket. Then, in the test bench, we drag and drop the reference on top of the test injection point. Upon starting a new Femap link session, we see that the imported geometry has changed. Looking at the log, we also see that the same interfaces are now mapped to different Femap IDs corresponding to the new geometry. Examining the rest of the model tree, we see that in addition to the created material and property cards just as before, a load definition was created corresponding to the force load construct in the test bench. Listing the constraint definitions, we also see that a fixed constraint has been applied to the surface associated with interface 4S1. This concludes the demonstration of how to set up a testing scenario in GME through the Femap application. Part 2 will go through the actual execution of a static analysis for this scenario.